Assalamu alaikum students. In this lecture, we will have a look at the concept of per unit system of measurements. Per unit system is basically makes the calculation is very easy when there is a transformer in the circuit. As we have already discussed in detail, when there will be transformer in the circuit, then it will be very difficult to solve the circuit. So this is another technique to solve the circuit which contains the transformer. This is called the per unit system of measurements. By using this technique, that is per unit system of measurements, we can solve the circuit easily. Now the question is, what is the per unit system of measurement? The per unit system of measurement is the ratio of actual value in any unit to the base or reference value in the same unit. It means if there is a actual value in voltage, then the base value should be in voltage as well. If the actual value in the ampere, then the base value should be in the ampere as well. Similarly, if the actual value in the ohm, then the base value should be in the ohm as well. So the formula of the per unit quantity is equal to actual value divided by the base value of the quantity. This is the formula. By using this formula, we can find the per unit value. We can find the per unit value by using this formula. The formula is quantity in per unit is equal to actual value divided by base value of the quantity. Actual value is the value in volts, amperes, ohm, etc. That is, actual value will be in the form of voltage, current, in the form of impedance, etc. And the base value, this is very important point, the base value will be multiple of 10 or power of 10. It means base value should be multiple of 10 or power of 10. That is, if the base value is 400, it means 400 is basically the multiple of 10. If the base value can't be 115, because 115 is not the multiple of 10. So the base value should be in the form of multiple of 10 or power of 10. Actual value can be 30, 20, 25, 21 in this form, but the condition for the base value is the multiple of 10 or power of 10. That is, let the value is 400. 400 is basically the multiple of 10. So we can select the base value 400. So let if the value is 117. So we can't select this value because this is not the multiple of 10 or power of 10. So base value should be or will be multiple of 10 or power of 10. Actual value can be any value. Can be 71, can be 75, can be 20, can be 30. The unit of the actual value, if the voltage in volts, if the ampere in the amperes, and if the impedance in the form of ohm. So these are the three quantities. That is per unit. We can find the per unit quantity by using this formula, that is actual value and base value of the quantity. And actual value is basically the given value in the circuit. The value given, the given value in the circuit is called the actual value, and base value, we will select the base value in the form of multiple of 10 or power of 10. So these 3 points are very important to solve the per unit system of measurement technique. So in per unit system of measurement, the voltage, current, power, impedance and other electrical quantities are not measured in their usual SI units. In per unit system, they are not measured in usual SI units, that is volts, amperes, ohm, etc. Instead, in per unit system, each electrical quantity is measured as decimal fraction of some base level. As we know, the decimal fraction is basically the fraction in which the denominator should be multiple of 10 or power of 10. If the denominator is the multiple of 10 or power of 10, then the answer of the per unit will be in the decimal fraction, because as we know, decimal fraction is the fraction in which the denominator is in the form of multiple of 10 or power of 10. So that's why the answer of per unit will be in the decimal fraction, and the answer of the actual value will be in the volts, ampere, and the answer of base value of quantity should be multiple of 10 or power of 10. So these 3 points are very important to solve the example, that is the per unit system of measurements. Now we will discuss the procedure of the per unit system of measurements. The step number 1. First of all, we will select two base quantities. As we have already discussed, base quantity is the quantity in the form of multiple of 10 or power of 10. It means, first of all, we will determine or we will select two base quantities. Usually we select the base values of the voltage and the base value of the apparent power. So normally we select the two base quantities in step number 1. The first one we select the base value of voltage V base, and the second one the base value of the apparent power, that is S base. Because the transformer is usually rated in apparent power, so that's why we select the base value of apparent power. The reason is that the transformer is basically usually rated in apparent power, so we can select real power as well. So in step number 1, when we will solve the numerical problem, in step number 1, first of all we will select the two base quantities, that is the base value of voltage V base and the base value of the apparent power, that is S base. The diagram of the transformer is shown here. As we have already discussed in detail, this is the secondary side of the transformer and this is the primary side of the transformer. So normally we select the base value of the one side of the transformer. By using these base value, we select the other side base values of the transformer. As we know, in case of transformer, the power remains same. It means in case of transformer, the primary power will be equal to the secondary power. It means the base apparent power in the primary side will be equal to the base apparent power in the secondary side. That is, S base primary will be equal to S base secondary. As we know, in case of transformer, the power remains same. Transformer does not change the power. Transformer does not step up or step down the power. In case of transformer, power remains same. Power can be real power, reactive power or apparent power. It means in case of transformer, the base power in the primary side will be equal to the base power in the secondary side. But in case of transformer is basically step up or step down the voltages. So due to this, the base power of the primary side of the transformer will be different as compared to the base voltage at the secondary side, because in transformer step up or step down the voltage, that is transformer changes the voltage. Transformer can step up the voltage, transformer can step down the voltage. So that's why the base value of the primary voltage will be different as compared to the base voltage at the secondary side. Now, the next step is step number 2. That in step number 1 we select the two base quantities, that is V base and S base. In step number 2 we will find the other base values, that is I base and Z base, the base value of the current and the base value of the impedance, by using these two base quantities. So as we know, S is equal to V into I. Apparent power is equal to V into I, that is S base will be equal to V base into I base. In step number 1, we will select the S base and I base. By using these two values, we can determine the base value of the current. So the base value of the current will be equal to S base over V base. By putting the value of S base and V base in this equation, we can determine the base values of the current. And the value of the Z base will be equal to, as we know, Z is equal to V over I. So Z base will be equal to V base over I base. V base we will select in step number 1, and I base we will determine by using this equation. So putting the value of V base and I base in this equation, we can find the base value of the impedance. So the other formula of the base value of the impedance is Z base is equal to, if we put the value of I base is equal to S base over V base in this equation, we get Z base is equal to V square base over S base. By using this formula, we can determine the base value of the impedance. So this is the step number 2. In step number 1, we will select the two base quantities, that is V base and S base. In step number 2, we will find the other base values, that is I base and Z base. So this is the step number 2. So in step number 3, we will find the per unit values. As we have already discussed, quantity of per unit is equal to actual value over base value. Base value we will determine in step number 1 and step number 2. And actual value is basically the value which is given in the circuit. The values given in the circuit is called the actual value. So in case of numerical problem, the circuit will be given. The value in the circuit is called the actual value. First of all, we will find by using step number 1 and step number 2 the base values, and then we will use the actual value which is given in the circuit. By using these two values, we can determine the quantity of per unit. So in step number 3, we will find the per unit quantities in each values. That is, if the actual value in the circuit is given in volt, then we will divide the base value of the voltage. So this is the important condition. If we will use the actual value of voltage, then we will use the base value of the voltage as well. If we will use the actual value of the current, then we will use the base value of the current. Similarly, if we will use the actual value of the impedance, then we will use the base value of the impedance. If we are using the primary side of the transformer, then we will use the actual value in the primary side and the base value in the primary side as well. If we are using the secondary side of the transformer, so if we are using the secondary side voltage of the transformer, then we will use the base value of the secondary side voltage as well. So this is the condition to determine the per unit quantity of the given system. This is the step number 4. So this is the step number 3. So in step number 4, we will calculate the actual desired value. So in this given numerical problem, the actual desired values we will find in step number 4. After solving the step number 1, step number 2 and step number 3, at the end we will solve the step number 4, that is calculate the actual desired values. As we know, actual values in this formula will be equal to per unit value into base values. So actual value will be equal to base value into per unit value. By using this formula, at the end we will find the actual values of the system. So this is the procedure to solve the per unit system of measurements technique. So these are the 4 steps. By using these 4 steps, we can easily solve the circuit which contains the transformer. So this is another technique called the per unit system of measurement technique. By using this technique, we can solve the circuit easily which contains the transformer in the circuit. Now we will do the numerical to understand all these concepts in much better fashion. After solving the numerical, we can understand all these steps in much better fashion. So the power system is given here. So the power system is given here. This power system is similar to the previous numerical which have done earlier. The diagram is same, which we have already solved in the numerical 2.1 in this chapter or in the last week lectures. There are 3 regions. This is the region number 1, this is the region number 2 and this is the region number 3. Region number 1, in region number 1 is the generator region. Then the transformer T1, this is the transformer T1. The ratio of this transformer is 1:10. It means the primary side, if the voltage across the primary winding is 1 volt, then the voltage across the secondary circuit will be 10 volt. It means this transformer is the step up transformer. In region 2 is basically the transmission line. And after this there is the transformer number 2, that is T2. And the ratio of this transformer is 20:1. So this is the step down transformer. That is, if the primary voltage is 20 volt, then the secondary voltage will be 1 volt. That is the step down transformer. And after this, the third region is the load, and this is the load. So this is the power system is given in this numerical problem. There are 3 regions. This is the region number 1, that is the generator side. This is the region number 2, that is the transmission line. And this is the region number 3, that is the load side. And there are 2 transformers, that is T1, this is the transformer number 1 and this is the transformer number 2. Transformer number 1 is basically the step up transformer and the transformer 2 is basically the step down transformer. We can find the step up and step down transformer by using the ratios, the given ratios. The first parameter is basically shows the primary side and the second value is basically show the secondary circuit value. So that's why this is the step up transformer and this is the step down transformer. So the base values are given here. V base is equal to 480 volt and S base is equal to 10 kVA. These 2 base values are given in this numerical problem. So this is the step number 1. In step number 1, as we have already discussed in the theory, in step number 1, first of all, we will select the 2 base values, that is voltage base value and apparent power base values. In this numerical problem, these 2 values are given. That is, Base value of the voltage is given in this numerical problem is equal to 480 volt, and the base value of the apparent power is basically equal to 10 kVA. So, as according to definition of the base value should be multiple of 10 or power of 10. So this is the value of the multiple of 10, and this value is also multiple of 10 as well. So these are the base values V base and S base which are given in this numerical problem. So the part A of this numerical is find the base voltage, current, impedance and apparent power at every point in the power system. So the part A is basically find the base voltage, base current, base impedance and base apparent power at every point in the power system. This is the given power system. It means in part A we will determine the base values in the generator region, then we will find the base values in the transmission region, then we will find the base values at the load side. So we will find in region 1 base value, in region 2 base values, and then we will find the region 3 base values. The base values are base voltage, base current, base impedance and base apparent power. There are 4 base values we will find in each region of the power system. This is the power system. So first of all we will find the base values at the generator region of the power system in region number 1. In region number 1, in generator region, there are 2 base values which are already given in the numerical problem, that is V base and S base. So V base 1 is basically in generator side region is 480 volt, and the apparent power S base 1 is equal to 10 kVA. These values are given in the given numerical problem. By using these 2 values, we will find the remaining base values, that is base value of the current and the base value of the impedance, because according to part A, we will find the 4 base values, that is the base value of the voltage which is given here, the base value of the current, the base value of the impedance and the base value of the apparent power. So base value of the apparent power and the base value of the voltage, these 2 values are given in the numerical problem. By using these 2 values, we will find the other 2 base values, that is the base value of the current and the base value of the impedance. Putting the value of apparent S base value and V base in this equation, we get the value of S base is basically 10 kVA and the value of the V base is basically given here 480 volt. After solving this equation, the value of the base current will be equal to 20.83 ampere. So this is the base value of the current. So now we will find the base value of the impedance. Putting the base value of the voltage and base value of the current in this equation, we get the base value of the voltage is 480 volt and the base value of the current is 20.83 ampere. After solving this equation, we get the base value of the impedance in the generator side of the power system is equal to 23.04 ohm. So in generator region, we find the base values of the current, base value of the impedance and the remaining 2 base values already given in the numerical problem. So now we will find the base values at the secondary side of this transformer. First of all, we find the base values at the primary side of the transformer 1, that is at this region, that is the generator region. So now we will find the base values at the secondary side of the transformer T1. that is the base value of the voltage, base value of the apparent power, base value of the current, and the base value of the impedance at the secondary side of the transformer. So now we will find in the region number 2, that is at the secondary side of the transformer. So the turn ratio of the transformer T1 is A is equal to 1:10. 1:10 means 1 divided by 10, and after solving this will be equal to 0.1. So as we know, Vp over Vs is equal to A. In turn ratio is basically equal to Vp over Vs. So in transformer T1, Vp is basically V base 1 and Vs is the V base 2. So Vs2 will be equal to Vp over A. Vp is basically V base 1. So V base 2 will be equal to V base 1 over A. Putting the value of V base 1, as we know, the value of V base 1 is basically given here 480 volt. And the value of A is 0.1. So after solving this equation, we get the base value of V base 2, that is in the transmission line region. The value of V base 2 is basically equal to 4800, that is 4800 volt. So this is the base value of the voltage at the transmission line or the secondary side of the transformer T1 in the given power system, and the base value of the apparent power will be same as the base value of the generator region. The reason is that in case transformer does not change the power, in transformer power remains same, that is power will be same in the primary side and in the secondary side. So transformer does not change the power. Transformer is basically only changes the voltage, that is step up or step down the voltages. So it means the base value of the voltage will change and the base value of the power will remain same because transformer does not change the power. So in transmission line region, base value of the voltage is equal to 4800 volt and the base value of the apparent power is equal to 10 kVA. So in transmission region, we named as V base 2 and S base 2. By using these two values, now we will determine the remaining base values in the transmission line region. The remaining base values are current base value and impedance base values. So I base 2 is equal to S base 2 over V base 2. Putting the value of S base 2 over V base 2 in this equation, we get the value of S base 2 is 10 kVA and the value of V base 2 is given here. As we have already determined, the value of V base 2 is 4800 volt. After solving this equation, we get the base value of the current, that is I base 2 is equal to 2.083 ampere. Now we will find the base value of the impedance, that is Z base 2. Z base 2 will be equal to V base 2 over I base 2. Putting the value of V base 2 and I base 2 in this equation, we get the value of V base 2 is equal to 4800 volt and the value of I base 2 is equal to 2.083 ampere. After solving this equation, we get the value of Z base 2 is equal to 2304 ohm. So these are the base values in the region 2, that is in the transmission line region. Now we will find the base values in the region number 3, that is in the load region. So these are the base values in the transmission line region or in the secondary side of the transformer T1. This is the transformer T2. These are the base values in the secondary side of the transformer. These base value will be same as in the primary side of the transformer T2. So now we will find the base values in the region number 3. So in region number 3, that is in load region, the turn ratio of the transformer T2 is, as you can see in this given power system, 20:1. So the ratio A is equal to 20/1. 20:1 means 20/1 will be equal to 20. That is, the value of the A is now 20. And in load region, the base value of the voltage V base 3 will be equal to V base 2 over A. That is, V base 3 is the secondary voltage, V base 2 is the primary voltage of the transformer T2, and A is the turn ratio. As we know, A is equal to Vp over Vs, and here the value of Vs is V base 3 and the value of Vp is V base 2. So therefore Vs or V base 3 will be equal to V base 2 over A. Putting the value of V base 2 and A in this equation, we get the value of V base 2 is 4800 volt and the value of A is 20. After solving this equation, we get the value of V base 3 is equal to 240 volt. So this is the base voltage at region 3. That is, the V base 3 is equal to 240 volt. And the value of the power, that is the value S base 3, will be 10 kVA. As we have already discussed, in case of transformer, power remains same. So the power, base value of the power will not change, because transformer does not change the power. So the base value of the apparent power will be same, that is S base 3 will be equal to 10 kVA. So this is the base value in region 3 of the voltage, and this is the base value in region 3 of the apparent power. By using these two base values, we can find the other base value, that is the base value of the current in load region and the base value of the impedance in the load region. So as we know, I base 3 is equal to S base 3 over V base 3. Putting the value of S base 3 and V base 3 in this equation, we get the value of S base 3 is equal to 10 kVA and the value of V base 3 is equal to 240 volt. After solving this equation, we get the value of I base 3 is equal to 41.67 ampere. Now we will find the base value of impedance, that is Z base 3. As we know, Z base 3 is equal to V base 3 over I base 3. Putting the value of V base 3 and I base 3 in this equation, we get the value of V base 3 is equal to 240 volt and the value of I base 3 is basically 41.67 ampere. After solving this equation, we get the value of Z base 3 is equal to 5.76 ohm. So this is the base value of impedance in region 3. So part 1 or part A has completed. We have find all the base values of the given systems, that is in the region 1, in the region 2 and in the third region, that is in load region. We have find all the base values. So this is the part number A. So part A has completed. Now we will solve the part B of this given numerical problem. So the part B is convert this system to its per unit equivalent. The part B is basically convert this given system into per unit equivalent. So as we know, we can convert the given system in per unit equivalent. As we know, a per unit quantity is equal to actual value divided by base value. So it means by using the actual values divided by the base value, we can convert the given system into per unit system in the per unit system form. So the actual value, as we have already discussed, actual value is the value which is given in the circuit. So in the circuit, the given values are the generator VG voltage, the line impedance and the load impedance. There are three parameters are given in the circuit. So this is the actual value of the voltage, this is the actual value of the line impedance, and this is the actual value of the load impedance. Base value, as we have already calculated in part number A, base values of all the regions. So we convert now. So now we will convert this given system into per unit system. As we know, in case of per unit, we will divide the actual value by base value. So the first actual value is the given voltage. The voltage in the given system is 480 volt. It means the actual value of the voltage is given in the given system is 480 volt. So voltage in the generator side per unit will be equal to actual value of the voltage divided by the base value of the voltage. The actual value of the voltage is given here 480 volt, and the base value, as we have already calculated in the part A, the base value is also same as actual value, that is 480 volt. After solving this, we get the per unit value of the voltage at the generator region is equal to 1 angle of 0 degree. So similarly, now we will solve, we will find the line per unit impedance. So this is the actual value of the line impedance. We will divide the actual value with the base value of the impedance, and by dividing this we can find the line per unit impedance. So putting the value of actual impedance, that is line impedance is given here 20 plus j60 divided by the base impedance, as we have already calculated in the part A at the secondary side of the transformer T1 or in the region number 2. Here we will use the base value of the region number 2 because we are using the actual value of the region number 2. So we will divide the base value of the region number 2. The base value of the region number 2 is, as we have already calculated in the part A, 2304 ohm. After solving this equation, we get the per unit line impedance is equal to 0.0087 plus j 0.026 in per unit. This is the per unit value of the voltage. This is the per unit value of the line impedance. Now the last value, actual value in the given circuit is the load impedance. So now we will find the per unit value of the load impedance. So as we know, per unit value of the load impedance is equal to actual value of the load divided by base value of the load. Now we will use the base value of the region 3 because we are using the actual value of the region number 3, that is Z load. Putting the value of actual value Z load is equal to 10 angle of 30 degree divided by base value of the region 3. The base value of the region 3, as we have already calculated, is equal to 5.76. After solving this equation, we get the per unit value of the load impedance is equal to 1.736 angle of 30 degree per unit. So these are the per unit values of the given system. So this is the part B of the given numerical problem. Now we will draw the equivalent circuit in per unit, in the per unit form, in the per unit system of equivalent. So now we will draw the per unit equivalent circuit by using these per unit values. So first of all, we draw the per unit value of the voltage. So per unit value of the voltage is 1 angle of 0 degree. So first of all, we will draw the per unit value of the voltage. Then we will draw the per unit value of the line impedance. The per unit value of the line impedance is basically 0.0087 plus j 0.026 per unit. So this is the per unit value of the line impedance. The third and last per unit value of the load impedance is equal to 1.736 angle of 30 degree per unit. So this is the per unit value of the load impedance. So this is the equivalent circuit of in the per unit form, in the per unit system. So this is the per unit equivalent circuit. So this is the part B of this numerical. Now we will solve part C of this numerical. So the part C of this numerical is find the power supplied to the load in this system. That is, we want to find the actual power supplied to the load. As we know, this is the equivalent circuit as we have already calculated in part B. This is the equivalent circuit in per unit form. So the per unit current will be equal to, this is the series circuit. According to Ohm law, per unit current will be equal to V per unit over Z total per unit. So V per unit in the given circuit is 1 angle of 0 degree, and total impedance in per unit is equal to, because the circuit is in the series, so we will add all the impedance. So the total impedance will be equal to 0.0087 plus j 0.026 plus 1.736 angle of 30 degree. After solving this equation, we get the value of current in per unit is equal to 0.569 angle of minus 30.6 degree per unit. So this is the per unit value of the current. So we can, by using this current, we can find the per unit power of the load. So the per unit power of the load will be equal to P, as we know, P is equal to I square R. So in power in per unit, P load per unit will be equal to I square per unit into R per unit. So here we finding the power in per unit across the load. So therefore, putting the value of I per unit and R per unit in this equation, we get the value of I per unit is 0.569 angle of minus 30.60. So putting the value of I 0.569 angle of minus 30.6 per unit square, and the value of the, because we are finding the power across in per unit across the load, so we will use the value of the resistance across the load. The value of the resistance is 1.503. We can convert this per unit value. This per unit is in the polar form. We can convert this polar form in the rectangular form. In the rectangular form, the real part will be the resistance, that is the value of resistance is equal to 1.503. After multiplication, we get the per unit value of the load across the load will be equal to 0.487. Sorry, in case of power, we only use the magnitude. We do not use the angle. So that's why we will only use the magnitude of the current. The magnitude of the current is 0.569. So the overall power across the load in per unit will be equal to 0.487. Putting the value of per unit in this formula, we get the actual value of the load will be 0.487 into base value 10 kVA. After solving this equation, we get the actual value of the load, P load, is equal to 4870 watts. So this is the actual value of the load across the load. So this is the part C of the given numerical. Now we will solve last part of this numerical, that is part D. Part D of the given numerical is find the power lost in the transmission line. So as we know, power in the transmission line, power line per unit is equal to I square R line. Now we will use the resistance of the transmission line. If we want to find the power across the load, then we will use the resistance across of the load. If we are finding the power loss in the transmission line, then we will use the resistance of the transmission line. So putting the value of I and R in this equation, we get the value of the I, as we have already calculated, the value of I is 0.569. Putting the value of I is equal to 0.569 square into the value of the R line is equal to, as we have already calculated, 0.0087. After solving this equation, we get the line power in per unit is equal to 0.00282. Now putting the value per unit and S base in this equation, we get the value of line power in per unit is equal to 0.00282 and the value of S base is 10 kVA. After multiplication, we get the actual line power is equal to 28.2 watt. So this is the part D of the given numerical. So that's it for this lecture. In the next lecture we will discuss the voltage regulation of the transformer and efficiency of the transformer.